welcome. I will post the solutions to these exams over the weekend, so they should be available by next week. And then you can go through, see if you have any questions with what you did and what the correct answer is. Make sure you understand. Again, you'll have that opportunity at the end of the semester to retake the exam to get a higher score if you would like. So you do want to make sure that you're mastering the material, making sure you understand what you might have missed from that exam if you were not able to be as successful as you thought you wanted to be. All right, any questions in general? Hey, last unit of material, like where are we? Exam 2, Exam 3. So the last material content is utilizing phasors to actually analyze the circuit. So this is where we're going to be looking at now, instead of just one capacitor or one inductor in the circuit, what if we have 5? It would be a 5th order differential equation that we would have to solve by hand, which is not fun, not knowing what this solution is going to be for 5th order. I do not know that one memorized. So we're going to learn these new techniques to now look at any circuit with any time-dependent element and be able to actually solve it. So I think it's a pretty exciting method that we are going to be working on. So the first thing that we want to do is see how can we actually do this. So the way this happens is that in the time domain for a differential ddt, it actually can be transformed into that frequency domain. One transformation is called the Laplace transform. Some of you may have come across this in your math classes, so now we're going to see how does this actually apply to this. So the nice thing about the Laplace transform is that in the time domain, that differential, this would be your time domain, and then in the frequency domain, this just becomes a variable, s. Makes it so much easier. I can multiply by s, I can divide by s, I can square s. So if I have it becomes a squared instead of a second order differential. So this is really a powerful thing. There's another one called the Fourier transform. And it does the same thing. In the time domain, it's a differential, and in the frequency domain, it becomes j omega. So what you notice here is that for our purposes, s can just be set equal to j omega, and it means the same thing for us. What is omega? It's the frequency from an input signal. So we would use that omega. And then we would have a complex number there, some number times j, and we now know, like, we can manipulate those expressions. So we need to look at kind of each of these elements. We already looked at like the input signal. This last test, you had to look at how do we transform that into that frequency domain. That was the phasor transform. And that really was just using Fourier. So for each element, a resistor is going to become, well, we're going to look at each of these. So each of these, as we know from Ohm's law, your voltage is equal to I times, if we call this just an impedance instead, it's going to be I times this impedance. So we want to know kind of what is this impedance for each of these elements And then can we look at them and they act like resistors? So each of these then can act like a resistance. So a resistor is going to just stay as a resistance. So let me do time domain. So to transform a resistor from the time domain into the frequency domain, that's just going to stay the same. So this is going to be in our frequency domain, is what we're trying to figure out what this value will be. We know for a capacitor that the current through the capacitor, actually put it on this side, is equal to C dVc dt. And remember, we said that you can just take the derivative, and so when we transform this, I becomes a phasor, C is a constant, so it just stays there. This then can become S times the phasor of Vc. So then Vc is going to equal IC divided by CS. So what is our Z in this case? It becomes 1 over CS, right? You guys see that? So this is the Z. And for frequency, or I mean for inductor, we know that VL is equal to L di dt. And so VL then becomes just L S and then IL, the phasor IL. So here, this becomes the impedance, L times S. So as I said, we can take S and equals to J omega. And these become specific values. So this can also be written as J omega C, and this can be written as J omega L. So if we know if we're looking at one specific frequency, we can just plug that in and multiply it by either the capacitor or the inductor, and we can get a value there with J. So it becomes now this imaginary, not imaginary, but a complex number. So if I have an inductor with a resistor in series, they're going to add together. And I'm going to have a real number from the resistor and an imaginary number from the capacitor or the inductor if they're in series. Parallel, they'll act just like we've seen in other parallel resistances. And we treat it just like a resistance, and we can use all the techniques we've used so far to solve for circuits. Questions about this so far? Okay. So one other comment, S is going to be used in a more generic form, and you can see with omega, once I know and want for one specific frequency, I'm going to use that form for the very specific value. Okay. That's it. Okay, so capacitor is going to be what? What was the equation? Okay, good. 1 over j omega c, which can also be written as, remember, 1 over j also can be equal to minus j. So I can write it as minus j over omega c. So it will be a negative complex portion. So looking at this, if I have really low frequencies, what does a capacitor look like? It's going to look like what? So the number will be really high, and so it will look like an open, correct? I'll just put like 1 over infinity is kind of going to be, if it's really, 1 over 0. With the limit goes to infinity. Put limit. If it's at high frequencies, it looks like what? I have 1 over infinity. What does that go to? That looks like 0, which is a wire. Thank you. So for an inductor, if I have low, what does that look like? 0, which will be wire. Good. And if it's high, it will also be high, right? Which looks like an open. What is omega for DC? For DC values? If I have a DC value, do I have any frequency to it? No, so what will omega will be 0, correct? So when you look at DC, so remember I said that you can use superposition. So you can use superposition to find the DC portion, and then you can use superposition to find the AC portion. So you zero out the DC, solve for AC, zero out the AC, and solve for DC. And so when you do that, you're going to put for DC, when you zero out DC, you're going to replace the capacitor with an open and the inductor with a wire. It becomes what we were used to, right? For the other one. So same thing as it sat there for a long time with no changes to the circuit. So that becomes easier to solve for the DC portion. Now for the AC portion, we're going to use this where we transform it into the frequency domain and solve the circuit in the frequency domain. And then we can add the two together. Okay? Does that make sense? And some yeses. Okay. All right, so let's look at an example. So this is from the book 7.92. So the first step in solving these is to look at the input signal. Do you have DC and AC? If you have both, then you're going to, for the DC again, you're going to keep the DC value, zero out the AC value, and then act like it's been sitting there a long time, replace the inductor, and just find the value of that. That's going to be your only single value you would need to find. Then for the AC, so this will be what we'll look at here. Well, maybe we'll do this. So let's say that this is plus plus 5. We'll do milliamp. Well, yeah. Okay, so we'll do 5 milliamps plus the 12. So this is where you need to identify, this is the DC portion and this is the AC portion. So this is the other reason you were doing that step, is a lot of times your signals will have a DC component and an AC component. And some of the time the AC component is not what you want in there. But you'll want to know what is the effect of that noise, or what is the effect of that signal that's been kind of forced into there doing to your overall circuit. All right, so for the DC solution, you are going to zero out the AC. And this is now just going to be 5 milliamps here. And then for IL of T, the DC portion of this, we're going to remove the inductor and then replace it with what? Wire. And then we're going to solve for the current here, IL. This will be your DC value. What will that be? 5 milliamps. So it's easy to find that solution, right? So a lot of times these are simpler to find for the DC. And then for the AC portion, we'll want to transform this. So we'll remove the DC portion. Here, remove AC. So here we remove the DC portion and we look at just the AC portion. How do we transform this signal into the frequency domain? What's the phasor of this one? Correct. And remember, it's 12 milli, because that can make a difference. So yeah, don't forget units. So we would do 12 milli e to the j minus 60, and then these are units as degrees. So now we're going to treat this like a resistor, but first we need to transform it. What happens with the resistor? Does it change? So it stays the same. It's going to be 20 ohms. What was the formula for the inductor? J omega L. And so L is 0.5 milli. And omega, we look back at the input signal, is what? I heard somebody saying it. Correct. 2 pi times 10 to the 4th. And now this is just an actual value. And it becomes 31.4 J. So now we treat it like it's a resistor with the value of 31.4 J. So with that, we can just, we're trying to solve for IL. I'm going to put my ground here. I'm going to just label this as an unknown voltage, and IL will be Vx over this 31.4 J. So then I can solve for Vx, and the equation for that is going to be that Is is coming in, so a minus 12 milli e to the j of minus 60 degrees plus Vx over 20 plus Vx over 31.4j. So now I have a complex number and I want to solve for j, or I mean for Vx. So I would do the same thing. And I can multiply by 20 and by 31.4 to get the common denominator. So 20 I don't want to solve that one by hand. Oh, sorry, there's a Vx here too. So this is where I would then go to a online calculator or my calculator. A lot of your calculators will do these now. So I just want to make sure the expression is still the same. Minus exponential minus I 60 degrees x over 20 x over 31.4, and that's equals 0. Okay. All right, that looks more correct. So this is giving it to me in either Cartesian form, or I could ask for exponential form. So in exponential form, this Vx then is, yes.
When you combine the terms, do you also have to multiply the -12 any j, any like, term by 20 and 31.4?
Yeah. Yeah. Thanks. Yeah. Thanks for catching that. So Vx is 0.202, e to the minus 0.48j, and this is what unit? Usually lets me see. So you need to make sure you know what units it's in. Okay, they've changed their screen. It's actually in radians. And then from here, IL is going to be Vx over 31.4j, which ends up being 6.4 milli, e to the minus j, and as I said, I like degrees, so I'm putting this back into degrees. So this would be my frequency, and answer in Phasor. And I can use the Wolfram. Alpha is what I tend to like to use. All right, this is minus, oh, so maybe I was not off, minus 117.5. All right, so now we want to get back into the time domain. So how do I write IL of t? So I'm going to take an inverse phasor to get back into the time domain. Cosine. Correct. We use the same frequency that we had in the signal, input signal.
Minus 117.5.
Correct. And there's my time domain expression. Yes, question? Yep, so this is the current going through that inductor over time. So it's this right here. So this is now describe the current going through the inductor over time. So previously we looked at this with a switch and we only looked at DC, right? We looked at the DC with a switch going in there. So the AC portion of that is a step function. So you can actually go back and solve these solve what we had done with the switch and instead put like U of t for if a signal is going on there. And you can do the same method and come up with the same expression as we were getting before. All right, questions about, so I forgot to add in, so this is the AC time. So the total one is going to be what? IL of t total. We have to add in the 5 millis, right? So it's going to be 5 milli plus the 6.4 milli cosine. So this is our full answer. Yes.
For like a task where we expected to solve like that big equation with
The one I jumped to, Wolfram alpha?
yeah.
No. So do make sure you know how to use a calculator to be able to solve for that. I would have something that's a lot easier to do by hand if I asked you to do this by hand. So I do expect you to know how to do the algebra, but more like what I asked in this last test of, being able to convert back and forth. And I'll probably ask that again because a lot of people miss that one. So to make sure you know how to manipulate to Cartesian and back into Phasor for simpler algebra. When it gets as complicated as this where, no, I won't make you do that on the exam. Okay, questions? Guys ready to try your own? Let's see. I think this one might be easier. Voltage. Node voltage. Okay, yep, let's just try this one. So this one's already been converted for you into the frequency domain. So if it's 2 amps and it's already in the frequency domain, what does that tell you about the input signal? Not DC, but it doesn't have any shift to it. So we're assuming it still has an AC component, but it just doesn't have a DC shift or an AC shift in it. Because remember, it's 2E, so cosine. So this will convert to this, and if phi is 0, that will become a 1. So it just means that the input signal, you can interpret from that the input signal is just no shift to it. So 2 amps and 4 amps are both cosines with no shifts. And they have the same frequency. All right, so this one I would suggest setting up as node voltage because you have 3 nodes that are unknown in order to solve for IC. And then I would use an online calculator, MATLAB, or your more sophisticated calculators to solve for V2 in that one.
Oh, okay. That's not gonna be safe. Okay, just do your.
That's.
Okay, so see a lot of people not really starting this, so what is the current here? What is the current through this point to J ohm? Correct. So it'll be V1 over, so V1 minus 0, because that's this one, over point 0.2J, or J.2. We know the current in this path. What is the current here? Can we just write it? There's no impedance in there, right? So we have to label it as an unknown. So I can call it IX. The current where IC is labeled is going to be what? Correct. V2 over minus 0.5J. This current is what? Correct. V2 minus V3 over 0.4. And then we have, this path has the defined current. So we're going to have we're going to have 3 node voltage equations. And then we need to, again, use, because we have the current only in one branch, we have 4 unknowns, right? Because we've introduced that IX. So where do we get that 4th equation for IX? Or related to IX? From the known voltage source, right? So we put it in terms of that value. So we know that the battery, we know V2 is a node and V1 is going to equal that value. And that will be our separate equation. Okay, now work on it. All right, so I wrote the node voltage equations at V1, V2, and V3. At V1, my first equation had this current, which is V1 over 0.2J, and it's going out. IX, which is going out, and then I had 2 amps that's coming in, so I did a negative 2 equals 0. So that's my first equation. For the equation at V2, I had IX coming in, so I did a negative IX. Then going down and out is V2 over minus 0.5J. And then going out again is V2 minus V3 over 0.4. So that one is at V2. And then at V3, I have 2 going out. And then I had this one coming in. So a V2 minus V3 over 0.4. And a negative 4 coming in, so or 4 coming in, so negative 4. I can also note that, I know 2 currents coming in or out, and then 1 unknown. So I can actually solve that right away to give me a minus 2 amps in that branch with the 0.4 ohms, if you want to do it with that already. So last equation is, because I had to label this current, I set the plus side to negative side of V2 minus V1 is equal to that minus 6J. If you like to look at it as, well, to go from 0 to V1 is a plus V1, then a plus minus 6J, and then a minus V2 equals 0 to give me that loop. Whatever way you like to look at that. Or I could say, well, going up to V1's plus, then plus through the voltage source is equal to V2. I can also say it that way. They're all the same equation, just different ways of looking at it. All right, questions on the setup of the set of equations? Everybody get this written down? Seeing some yeses? Okay, good. If not, make sure you go and understand, meet with the TAs, come meet with me, make sure you do understand node voltage and how to write those equations. I then used Wolfram Alpha, and the new interface is a little bit weird, so when I did the underscore, like V_1, it was doing something weird. So I used A for V1, B for V2, C for V3, and X for IX, and then Y for that IC value. And then I just made sure that my equations were the same as this equation set. First time I typed it in, they were not, and so I went back and fixed it, and then was able to get these answers. So Y in this case ends up being 17.333. Questions? What if I want to write IC of T? What will that be? So this is in the frequency domain. So I need to take the inverse phasor of this. So that would be what? And we don't know the frequency, so I'm just going to leave it with omega. And then there'd be no angle there, because it's only the real component of it. So this would be my I of t, or IC of t. if I was to write the voltage V2 of T, V2 in here was the variable B. How would I write this in the time domain? What is minus J translate into? So I guess the first step here would be to what form do I need to get? This is in Cartesian. So what form do I need? And you need what? I can't hear you.
Polar.
Thank you, polar. So we need polar. So minus I is the same as minus J. So what does that transform into polar? If I don't remember, I can just take 8.66 cosine. Oh wait, sorry. It'd be square root of 8.66667 squared plus 0 squared. Oh, we can't do, yeah, I can't do it this way. So here I just need to, because it's a negative J, I just know that it's e to the 90. So this will be what? Go for it, Zach. Correct. So that would be the time domain expression for V2 of T. All right, questions on this? For C, which is V3, so if I was to write V3 of T, I need to first convert that into full polar form, and then I could transform it into the time. Yeah.
So why is negative 8.6667 negative J equals e to the negative J? Like, how does that turn into that?
This is easier to see visually. So polar form, you have your real and imaginary axis. And what polar form is it's describing a vector on this plane. We describe it as the vector length and then the angle. So when we have an angle that's straight up, what is this vector described at in polar form? Say it just has, it goes to 1. It would be what? It would be just 1 times EJ90, right? Same concept if it goes down, it's going to be whatever magnitude is that. And then the angle is a negative 90. So this is, so if it's a negative 1 here, then this is going to be negative 1 E, sorry, it's still 1. It's still the magnitude, which is 1, E minus J90. So the magnitude is always positive. So the magnitude of that one is still 1, even though it's going in the negative direction. Does that make sense?
Yeah.
Okay, so magnitude is still 1, and then the angle is a negative 90. So that one's easier to see visually. Okay. All right, other questions, comments? It's ready for another one? Okay. Find the voltage here. We'll call it Vx between A and B. So this one, you do need to convert each component into the time domain first. So first step's going to be converting it to the frequency domain. Next step, I would label your nodes, and then I would probably do node voltage again. And then notice that A and B are floating wires. So if you I'll let you try and figure it out first.
Resistance is what's differing others in my mind. Whatever J is. I just said I said how did V8 put it out with it? Source the V8. I just like oh yeah.
So the conversion, it looked like most of you had gotten this done, so hopefully you did it correctly. So for for every resistor, it's going to stay the same in the frequency domain. So 25 stays 25. The 1 millihenry becomes J omega L, and so you have to identify what is your omega. Omega in this case is defined by your input source. So that omega is 4 times 10 to the 4th. So that one will be J times 4 times 10 to the 4th, and then 1 milli is 1 times 10 to the minus 3 for 40 J. For the capacitor, the 0.5 microfarad, that becomes 1 over J omega C, and then that multiplies out to be a 50 over J. So that becomes 50 over J, and then remember the property of J is that 1 over J can become a minus J. So I bring that up to be a minus 50J. Any questions about these conversions? Okay, the phasor, you have no angle there, so it becomes 3 EJ to the 0 degrees, and E raised to the 0 is 1. So this goes to 1, and so this just is 3. So my new circuit is going to be 3 amps here, 40J, And here is a minus 50J. And this one is going to stay the same. So this is your new circuit. From here, I would most likely solve this with grounding this node. Noticing that this is open, so this would be 0 current here. So whatever voltage I get across the capacitor here is going to be Vx. So I would label just one node, do node voltage, find Vx, and then find the current, or you can define everything with another node and then find that node voltage, either way. But this current will be Vx over 35 minus 50J. So this would be how you write that. And then, oh, sorry, this is both Vx. I didn't realize that. Sorry, let me call this V1. So V1 over 35 minus 50J, and then Vx is going to be that current times a negative 50J. All right, so work on solving the rest of this for Vx. Let you guys have a minute to solve for that. Since we're using calculators in here, this is more likely going to be easier to do with labeling this as Vx and just writing those two node voltage equations. And then just use the calculator to solve for them instead of manipulating it 3 times. So with using Vx in there, what is the current in this branch if I label it this direction?
My normal calculator could not do that.
Correct, so it's going to be V1 minus 0 over 25 plus 40J. And then the 3 amps is defined. What about this current? Correct. V1 minus Vx over 35 here. And then I'm going to erase this one. This current. Correct. So you're going to have 2 equations here at V1. It will be the V1 over 25 plus 40J minus 3 plus V1 minus Vx over 35 equals 0. And then at the Vx node, it's going to be a minus of that, V1 minus Vx over 35 plus Vx over a minus 50J. And then plugging that into the calculator. So I used, get this over here. So I used A was V1 and then X is Vx. So this resulted in my Vx is this one. If I want to write Vx of t, what do I need to do? Correct, so I need to invert it first into the polar form to convert it. So that is going to be the square root so I have a minus 44.595 over 107.432. And that ends up, well, using my calculator. Is it arc? Can't remember if it's arc 10 or. This does. So 116.32 e to the negative j minus 22.54 degrees. So let me go back this way. So what will that be in the time domain? What was omega? 4 times 10 to the 4th. So that is my time domain expression for Vx of t. Okay. All right, questions? Anybody get this? Get close?
So to clarify, like on an exam, we'll probably have a question like this where we have to use Wolfram Alpha, and we might have a different question where it's like manual computation.
So I'll probably break it up so you can do it on paper. So you would need to write the expressions such as this. If I had you solve this by hand, it would be something like you saw in this last exam where you would convert it, add, subtract, multiply, and divide, and then be able to convert it back. So it, correct, you won't have to use Wolfram Alpha on the test. And then I could ask you, given these results, transform them back into the time domain. So being able to do those steps of it. One thing to note here is that you could, if you were trying to find the Thevenin equivalent of this circuit, this Vx would be your VTH. So you do this same method as we used before, is you have a location of A and B, and now your result for VTH, and now it's going to be called ZTH for, it could be a complex impedance that you're solving for. So if this was to find, the actual Thevenin of this, we have now so we already found VTH of this. That's going to be what Vx is. So VTH in polar form is that 116.32 e to the minus j 22.54. And now we call it an impedance, ZTH, instead. So to find ZTH, we're going to use the same method as we did before. Any sources we're going to remove, independent sources we'll remove. So this becomes an open. I'm going to replace these by the frequency equivalent, so 40J, and this was minus 50J. We will combine them just like they are resistors. And so these are all in series. So this now becomes 25 plus 40J plus 35 for 55 plus 40J. 60, yeah, thank you. Yeah, 60 plus 40J. And then that component is in parallel with the minus 50. So ZTH here is 350 over 37 plus this 60 plus 40J in parallel to a minus 50J. You're going to keep that 60 plus 40J as one component together. And so this in parallel looks like this, 1 over the quantity of 60 plus 40J plus 1 over the quantity of minus 50J. You would put that into a calculator, and then that will give you your result. So moving to, again, Wolfram alpha, or a, so we have 350 over 37 plus 1 over 60 plus 40I. One over a minus 50 times I. And make sure it interprets it correctly. So 350 over 37 plus 1 over the quantity 60 plus 40, and then a minus 150. And that ends up giving us this, which is in the polar form. So, okay, here it is. So 50, so in ZTH, we want to have this in rectangular form. So this ends up being 50 minus 43.24J. What are the equivalent components here? $50 would be, look like what? Just a normal resistor. So a resistor of 50 ohms. What is the minus 43.24 going to represent? Has J in it, so it's going to be which options? Capacitor and inductor, and it's negative. So it's going to be capacitors. So the capacitors contribute a negative complex, and the inductors contribute a positive complex. So those are really useful to know if you're trying to shift signals and either change their frequency. You have control over that by using an inductor or capacitor. So there's some really cool circuits that you can add onto an equivalent. So a lot of times this would be some black box that you're measuring, and you're like, actually, I don't know what the components are in there, but I can model it as a complex component, and I can narrow it down to, okay, if this is kind of what my result is from my testing, I have a resistor, and then I know it has a capacitor of value minus 43.24J. And so now I can say, well, I can work with that. I can either compensate for that inductance effect, or capacitor effect, if I don't want it there. I can add in an inductor to compensate for it and get rid of the complex portion of it. Does that make sense? So if I added on here a capacitor, so we know, let me show you what I mean by this. So if this is our equivalent model for whatever system we have, I can actually get rid of the complex portion by just adding on an inductor before whatever else I want on there. And if I put it at this same exact value, it compensates and actually removes that complex component to it. So there's ways of reducing this and shifting things back to like where there's no AC contribution as far as the shifting of it. And then unfortunately not all systems are nice and stays this value. They'll only stay this value for one specific frequency. And so they may even change over frequency, they may change values. And so that's what makes things a little bit more complicated. But this gives you still the idea that at a specific range of frequencies, you could compensate it for, you know, sort of compensate it as much as you could to get rid of some of the effects if they weren't effects that you wanted into a system. Does that make sense? Okay. All right, I think we have time for one more. Yep, okay, we'll do this one. This will be our last one for today. You guys are getting lots of practice in. Okay, 7.40. Does it help to know this is actually all the content that you guys are going to have in this unit? So now it's just solving these more complicated circuits. So the other thing we haven't, so this one, I think I want you to solve for the Thevenin of it. What?
Does that mean the rest of the lecture would just be review?
Mostly, yep.
Okay.
Yeah, yes, and I'll try and address other concepts that seem to be needing a little bit more help. So if you have any, requests, feel free to bring them up.
There's no one thing I can keep my
So what's the first step in solving such a problem? Good job, yes. Transform it. So transform those signals and then transform the inductors into capacitors.
I do that so often. I just know what the numbers like to look like, and I don't know what it's called.
What?
ES and
So they're your signal here, signals. So VS and IS.
IS. Sorry.
Or were you just asking what values they were?
I just couldn't see it, so I
Oh.
had to write it down.
Okay.
Oh, yeah. Oh.
Wait, capacity?
I got a 100 for the Y.
Oh, wait, I did not.
No, you're so right, it's only
But if the.
Oh, yeah.
and then it's just one for the.
It's 100
But that's gonna be.
for the inductor.
So for the capacitor. Cause this.
Oh, is there a negative?
Yeah, 1 over JWC. That's what she said. The JWC.
Well, it's for.
Oh, right.
Yeah, cause I
It's
just.
25.
J over WC.
It's 4 over.
Are we getting V Thevenin as well, or just D Thevenin?
Both.
Both?
But then the.
You need like a board.
As an equation, yeah.
Oh, yeah. I was kind of, like, I figured I'd be fine with it. And I compared some of the
Since it's just so you know what the existing
Oh, true. So I guess we don't even need I. Yeah, so we just.
Right, because it would be different if just it wasn't brown. But yeah, so this.
What else did you need? Or are you just putting all of these?
Yeah, it is. You only have two.
So
Yeah,
I think he was also IX or.
No, there would be some I, but like, I don't think it's this first grade, but I'd be able to just.
What is it, 10, 10J, 12?
So you finished. I think that. So I think we just have our.
So I did this node, right, and then this node. Sorry, did you define your like this?
The way I do it is I always start in the middle of the out. So,
So, well, I guess that's a notable thing. So you like, how do you try to find the voltage?
for PA.
Except they already give you. Well, you're missing one. Yeah.
Or, oh wait, yeah, for you're at a DC. So. Maybe let's just play it out of it.
All right, so using node voltage, I defined all the currents going in each branch. So at Vx, it's going to be this one, Vx minus 12 over 10J, this one, Vx over minus 5J, and this one, Vx minus VTH over 10J. In this one, I have to do a minus of this one, which is a minus Vx minus VTH over 10J, which is this one. This one, which is VTH minus 12 over 5. This one coming in is a minus 0.5 e raised to the j to the minus 30. This one is VTH over 10. So using Wolfram alpha, that ends up being that my VTH is a minus 12. So this is my VTH. So it has no complex component to it. And then for ZTH, I have the 10 ohms in one branch, and then everything else can be combined into the other branch. So I have to combine all this. So, oh, sorry, this is going to be 10 in parallel. I miswrote that. Oops. So this is 10 in parallel with all of that. And then it's going to be 5 ohms is in one branch. And then this branch is going to be 10J. And then it splits. So it's 10J plus 10J in parallel with a negative 5J. Plugging that in ends up being 0. So if you didn't get these values, try to figure out what you did wrong, and then we'll talk about it on Monday. All right, if you didn't pick up your exam, please come and pick up your exam.